Fellow members, ladies and gentlemen, good evening and a warm welcome to the public lecture of the Hong Kong IE Outstanding Paper Award for Young Engineers and Researchers 2023. We are glad to have all of you here today, both at the Hong Kong IE headquarters and online, demonstrating your support for the impressive achievements of our young engineers and researchers. The Hong Kong IE Outstanding Paper Award for Young Engineers and Researchers is an international paper award organized annually since its first launch in 2006. This award encourages young engineers and researchers to develop innovations, technologies, publish their achievements, and to promote the engineering profession among the younger generation. This award is open to young engineers and researchers aged 35 or below worldwide. Now, may I introduce our first awardee, Dr ZHU Ke. Dr. ZHU is now working in the Hong Kong Electric Company Limited for studying and developing the smart grid in the power transmission and distribution sections of power grid. He will present his awarded paper on use of insulation resistance imbalance degree for the condition assessment of power distribution cables. Let's welcome Dr. ZHU.
Thanks, Chairman. Thanks for your kind introduction again. And good evening, everyone. So I would like to welcome all of you again, either joining this seminar on site or remotely. So today, my presentation title for this seminar is Use of Insulation Resistance Imbalance Degree for Conditionally Assessment of Power Distribution Cables. Overall, this is a technology for diagonalizing the power cables of a power company, so which are a critical assets of our company. And I'm not sure if you are working in the area of power industry, but if you are, I wish that after this seminar, you can validate the efficiency of this method. But if you are not, I hope that you can learn something about what we are doing in the past years to achieve a reliable power supply for our customers. Okay, so I will go ahead. Okay, so this is the outline of my seminar. So the first part, I will give you some knowledge about Hong Kong Electric, or also the background of the power system. And I will introduce the critical assets, the underground power cables in our company, and what method that we use to identify its carelessness. And also, I will introduce a very important method called the insulation resistance test, and also present its weakness and how we tackle it with our proposed methodology. The last part, I will give you some demonstration to verify its effectiveness. Last but not least, I will give you a conclusion. So the first part is about Hong Kong Electric. Actually, Hong Kong Electric is one of two power companies that are supplying the electricity for Hong Kong. By looking at the map, that you can see the governing territory for our company is quite small comparing to the north parts. But so we supply the electricity to the Hong Kong Island, and our electricity is generated from the Lamma Island. Though very small, but I would like to say that our company is very important because Hong Kong Island has so many commercial and financial centers located along in the north parts of Hong Kong. So we must ensure a very extremely high demand on the supply, reliability, and the power quality. So what would be a structure of the power system? So power system actually, I say it can be divided in three sections: the generation, distribution, transmission, distribution, and our customers. So it converts a kind of energy, such as coal, into the electric energy. Okay. So indeed, the high reliability of a power supply cannot be retrieved without a very reliable transmission and distribution system. So in our company, that's we majorly use the underground power cables. The reason is why that because Hong Kong is a coastal city and the underground cables are less prone to the adverse weather such as typhoon. But does that mean that the underground cables are free from any faults by overlaying in an underground way? I would say the answer is not. So here is a summary of that some defects that we observed to our underground cables. So the cables may still experience a tripping if the defects occurs. Okay. So there are several defects that the following three defects that are shown as follows. The first one is water ingress due to the poor water flow capacity. And the second is water tree growth in the cable body. And the third one is because these cables are overlaid in the underground together with other pipes, so there can be damage. Okay, so if there is a damage, the water can have some water ingress and finally lead to the cable fault. So in order to actually evaluate the several technologies that are used in this area in the power company. Okay, so first one is about the partial discharge. The principle is that when there is a dielectric breakdown of a small portion of electric insulation, and together with a high voltage stress, the cable will generate the partial discharge. In our system, that we installed the high frequency custom current transformer to capture the signal. The second one is the dielectric loss measurement. So it measures the insulation level between the cable conductor and the sheaths. Okay, so the dielectric loss, if you increase its magnitude, the cable insulation degrees. And actually, Hong Kong Electric has began to do very low frequency to assess the cable conditioner about 10 years ago. The third one is very popular and easy, and it is called insulation resistance measurement. Okay, so it evaluates the insulation level between the cable sheath and the conductor. So we conduct this test before the cable commissioning. And I would like to recommend this one because it's very portable by using an ohm meter and very easy to carry. So what's the process of this measurement? So actually the cable first need to be offline, and then we discharge all potential stored capacitance in the cable. Then we can conduct the measurements. Actually our cable are three phases. So we first measure the insulation level between the conductor and the sheath for one phase, and together the same principle applies for the other two. Okay. So you have the three-phase insulation. The problem is that, this method is very easy, but the problem is that how to define a constant and efficient threshold of assessing the power cable, the condition. This is because that this value is very hard to define because our circuit is very complex, composing of different cable type, cable length, the types of cable joints, and it's several years, etc. Okay. So in order to tackle this problem, we propose a new concept called the IR imbalance degree, and I will introduce in this part. So first, because here are some assumptions. That's why we can use the IR imbalance degree to evaluate the cable, the hairless of the cable. So in principle, the IR measurement of three phases should be homogeneous if the cable over perfectly and laid properly. Okay, so that means the IR measurement for three phases should be identical. Okay. When a tiny defect generally originates, and then the phase, the insulation, the IR began to decrease, and then you can see when the defects evolves globally, and so we can use the IR measurement, the measurement of surfaces to identify the hairless of the cable. So what's the equation of this? So you can see the lower part of this slides. So the upper part the lower part that we measure the three-phase, the average of three-phase IR measurements. And in the upper part that we evaluate the deviation from one phase to the average. Suppose that we have a very hairless cable and the three-phase IR measurement is balanced, so the value will be 0. So what will happen that if one phase and two phase, even surfaces become the degraded. So here are some mathematical derivation. So in one phase, by looking at the equation, we assign different coefficients for three phases. Supposing that the unit, if three phases has a unit value, and the coefficient for phase begins to deviate. Okay, so now the value by the calculation it will arrive 100%. And the same derivation, if you are interested, you can look at my paper, and the value actually will reaches 200%. Okay, so it states that the cable, so you can see the left part of my graph. So it describes the IR imbalance derivation from the paired cable to a one-phase imbalance, two-phase imbalance, and three imbalance cases. Okay, So the IR imbalance value will become from 0 value to 100 and the most serious case to the 200. Okay, so this is the what's the range of the IR imbalance degree. And actually, in Hong Kong Electric, in the past 10 years, we have like 5,700 testing records, and you can see the distribution. That I would say most amendments that are distributed under 100%, but there are rare cases that locating between 100 and 200. That is the severe case that we need to pay attention. Okay, so actually from this distribution, the question is that how we can find the threshold of our IR imbalance degree for a cable hair series. So of course that actually you can use some mathematical method or some AI method to see the distribution of this graph. But for the easiest use of our engineer, that's we easily adopt the Pareto principle. So the principle that I think if you are familiar with some physics, so it describes that the 90% of consequence of this world are derived from the 30% of the causes. Okay, so that's we set a very easy threshold for the criticality. Okay, so then if you look at the right graph of this figure and it plots the number of tests and the distribution of an IR imbalance degree. So if actually when the cable becomes one phase imbalance, we need to pay serious attention. This is because that what phase two ground faults actually happens very frequently in our system. So we set the threshold from the deviation from 100 to is 10% deviation, and then we got the threshold should be 75%. Interestingly, we also look at the insulation resistance measurements, the absolute value of all the IR measurements. And because that, when an IR is smaller, the cable is more dangerous. So we set the 10% threshold from the 0 value, and we got a threshold of 0.15 GOhm. These two criteria, we form a judgment on the right lower part of this slides. So if the IR balance degree is larger than 50% and the IR measurement is less than 0.15 GOhm, the cable needs a serious attention. And if either of the two matches, that's the cable needs a further advancement. Okay, and if these two criteria does not meet either, and we don't have to any action on the cable. So this is the criteria that we form for the cable diagnosis in the IR measurement. Will this method effective? So let me give you some examples. The first one, but before that, let me give you some information about our underground cables because you may not be familiar with that. So you can see there are two substations, and the cable actually is not overlaid strictly by a cable body directly. So there can be a different type of cable bodies, and there can be different number of cable joints. So for the cable bodies, there are major two types. They mainly refer to the insulation, different insulation material between the conductor and the cable sheets. There can be oil cable insulation or the XRP insulation. Okay, and also because you can see the cable are connected by the cable joints, and then in different area in the history we have different cable joints, and there are mainly three types, and their description are listed here. So the first one that I want to give you is that the cable needs a serious attention. So you can see the left part is our setting of this cable, and it consists of two joints and three cable sections, and there are PRLC and also mixed with XLPE cable bodies, and its length is dotted on the graph. So we have the IR measurement, and in this case that we say that the two criteria are matched. Okay, so it denotes that the cable needs a very serious attention. So under the case, what are follow action? So because the cable is very dangerous, and we apply the voltage above the normal operating voltage to adjust the cable situation in a prescribed manner of a set of period. So that is called a monitored withstand test. Okay, so we apply the 2 times rated voltage and a 30 minutes monitored withstand test on the cable. And actually, we found that the cable of L2 phase 40 during this test. So it verifies that the cable is very weak. So actually, we use the fault location method to explore the faults, and we return the faulty component, and we find that the cable has a prolonged water ingress in the cable. And from the signs that we observed that the outer jacket of the joint was found to be damaged on one side of the cable. So that why the cable, the air alignment for this cable is very weak. Okay, so this is the first case. This demonstrates the effectiveness of our method in the situation one. And the second one is also I would like to give you, which deserve a further study. So in the left part, you can see the demonstration, the setting of this cable, and also we can see the air alignment on the right-hand side. So the air alignment actually is very large, larger than the 75%. So so by the same principle that we have gone the cable with MW test, but the cable does not fail. So it means that the cable is somewhat robust. Okay. So but actually we wonder why the TD measurements, the dielectric losses is imbalanced. So we also conduct a partial distribution mapping, and then we find on the termination of the cable that it suggests that there are concentrated partial discharge. So we check and cleaning the cable termination, and then do the IR alignment again, and the IR alignment becomes balanced again. Okay, so this is the situation for the second one. The last one is that the symbol I would like to demonstrate is that no action required. So you can see the cable setting as well, and also the insulation resistance measurements. And because all these two criteria does not match, so there is no action needed. So in these three cases, that we demonstrate that the effectiveness of our proposed method by identifying the cable healthiness by using the IR imbalance degree. Okay. So last part is my conclusion. So this paper introduced a new method for the conditional assessment of the medium voltage power distributed cables based on the conventional IR test, but with a new data analysis approach. The second point is that because having this method, that because there are hundreds and thousands of cables overlaid for our company, so by this measurement, we can prioritize the maintenance efforts of these cables. The third one is that this method actually is not only for these 11 kV power cables, and can be also applied for the airway or higher voltage cables. So this method can be applied for the other cables potentially. Last but not least, this improved inspection tolerance could further enhance the reliability and security of the Hong Kong electric power supply. So this is all my part, and thanks for your attention.
Thank you, Dr. Zhu. Let's move on to the questions and answer sessions. We have 10 minutes to answer questions from the floor and online. For the online audience, if you have any questions for Dr. Zhu, please put down your questions by using the Q&A feature on the screen. We will attend to your questions shortly. Okay, now may I invite questions from the floor here. Any questions? Yes, please.
A very simple question. I would like to know if your proposed method has actually been used in practice.
Yes, actually the IR test, as I said, that it has been the power company for many years. But in the past, we just don't know what threshold that we need to apply. So we have this requirement, but actually how to apply it is a problem. Okay, now actually we apply it simple, and we look at all the historical data, and also in the future every combination test, we are using this method. Yeah, so it's very applicable and useful for the electrical engineering, and can be applied very quickly. Yeah.
Okay, I also have a question. Okay, well, I am not an electrical engineering expert. Okay, but As far as I know, there are some power quality issues in the cables. For example, harmonic distortion or poor power factors. Okay? If this occurred, would it affect the accuracy of your fault detection?
Actually, the harmonicas occurs because that you may have the not pure resistance load. Okay, so I think when when the load increases, the thermal effect will happens on the cable. Yeah, so which will lead to the cable faults. Yes, I think there's some relation between the fault occurrence and the harmonics.
Okay. Let's see. Okay, maybe I can ask one more question. Okay, here in the conclusion, the last item, okay, you mentioned that it enhances reliability and security. My question is, does it enhance the energy conversion efficiency of the power grid?
Of course, I think that if the fault occurs on the cable tripped and the customer will lose the power supply. So if we can avoid the interruption of the cables, I think the power delivery will be very smooth. And in that way, I think the reliability and the quality of the electric delivery will be very, very, very great. Yeah.
Maybe one more question. What is the implications for the economic benefits of this technology?
Yes. So actually, when a fault occurs, that we will put efforts and monetary efforts to rescue the cable by replace a new component. So we have to do investments for the rescuing work. Okay. The other part is that I think the most the effect that influence is by our customer. So we don't want our customer to lose any electrical supply. So I think that is the most beneficial part for our customer.
Okay, we have one question from the online audience. Let me read the questions. Okay, what are the constraints of this method? Let's say the length of the cable or the number of joints or what are other potential constraints that limit
yes,
your method?
Actually, we see some cases that fall in the serious condition of our diagnosis results. And once we apply the MWT and also the pressure test, etc. as well, but actually the cable does not fail. So there are some cases that actually in the severe situation, but we can't locate the defective component. So actually, the further location of the fault by falling into this criteria that deserves further investigation. So that's my answer. Yeah, we are still exploring some parts of it. Yeah.
Okay, so well, we have already asked a lot of questions. Okay, and all the questions have been answered very well, okay, by Dr. ZHU. Let's thank Dr. ZHU. Okay. Okay, let's proceed to the presentation of the next awarded paper. May I introduce our second awardee, Dr. LI Quankun. Dr. Li is now an associate professor with the School of Power and Energy at Northwestern Polytechnical University. Here to join the lecture this evening. He will present his awarded paper online, and the topic is a novel nonlinear vibration feature-based approach for evaluating both loosening fault in aerospace structures. Let's welcome Dr. Li.
Okay, thank you, Chairman. and I will start the presentation. Good evening, ladies and gentlemen. Thank you very much for your coming, and thank you very much for the assistance from the HKIE. It's a great honor for me and my partner to participate in today's public lecture. I'm Li Quankun from the Northwestern Polytechnical University. Currently, I'm an associate professor, and my research interest includes nonlinear dynamics, vibration control, condition monitoring, and fault diagnosis. And this is my WeChat account, and this is my telephone number and email address. If you have any question, you can contact me for the further discussion after the presentation. Okay, let's back to the topic. Novel nonlinear vibration feature-based approach for evaluating both losing force in aerospace structures. This work is completed by me and my previous supervisor from the City University of Hong Kong. And there are 5 members. As shown in figures, for some aero engineering structures such as rockets, satellites, aircraft, and engines, both and last are frequently applied to fasten different components together. However, these bolted structures often encounter dynamic loads in the service process, such as the vibration, shock, or thermocycles, and which in turn cause both losing force, which will affect the smooth and normal operation of structures. Therefore, it is very important and critical to use some methods to diagnose both losing force in these structures, especially at their very initial stage. For this objective, there are many methods based on vibration features. Today, I would like to introduce the transmissibility function. According to the output responses used for the definition of TF, there are 3 main types of TF. Compared with other vibration features, TF has obvious advantages. Firstly, it is defined as the ratio of output spectrum, which means no need to measure the input, no need to do the identification for model parameters. Secondly, since the TF is just a function of the structural local parameters, which means it would be more sensitive to force in structures. However, for existing methods, there are still some limitations. One is about the structure. Actually, most methods are more applicable to beam-like, very simple structures such as the beam-like, rain-type, or grid-like, and they consider a little for the complex aerospace structures. The second term is about the nonlinear boundaries, which will be coupled with force, but most methods ignore them. And the last term is about the entire model and the data of the structure. Actually, most methods require a reference data or reference structure for the damage diagnosis. To overcome these limitations, we propose a novel method for complex aerostructures with nonlinear boundaries, and we only consider the structure we care, and we only consider structure to be diagnosed. We don't use all the data from the structure. Actually, in real application, it is a little hard to know the parameters of the entire structure or measure all output responses from structure. So in our method, we decompose the complex structures into a series very simple T-type substructures to simplify the theoretical analysis and data processing. And in the model or in the structure, we consider both losing force and nonlinear boundaries. And we only use output responses from the T-type structures to to be diagnosed to get two photo pictures and a novel indicator. As shown in the figure, it is a bolted satellite structure which is collected by some beams and bolts. And as highlighted in the circle, we can find some T-type substructure, and we can also get its multi-degree of freedom model. This is the center mass, and these around mass are collected with the center mass with some spring and damper collection. And in this model, we use the nonlinear collection to simulate both moving force. And for this T-type structure, we can find many T-type structures in the entire structure, and we only consider the structure to be diagnosed. And we will use these four output responses to decide whether there is a both moving force around mass mi. Okay, then for the structure, we can get its differential equation of motion. This is the mass mi, and this is the acceleration, the velocity, and this is the displacement. And C and K represent related damping and strength stiffness coefficients. And this term represents the nonlinear force caused by both moving force in the structure. And actually, it has many informs, and we consider the common form, which is a polynomial function of related velocities and displacements. And there are some extensions for some parameters. Actually, this one is very important for method, but we don't consider its detailed type. We consider its value. Actually, if there is no fault in the T-type substructure, then related nonlinear force will be zero. On the contrary, if there is fault in the structure, and this nonlinear force term will be non-zero. So we will use the value of the nonlinear force, zero or non-zero, to determine whether there is a fault in the substructure. Use the harmonic balance method, then we can assume the nonlinear output responses of the structure and substitute this responses into the Fick's domain equation of differential equation. Then we can get the Fick's domain equation, and with some operation and the definition of the transmissibility function, then we can get a brand new equation. And these are structural parameters, and these are structural parameters, and these are transmissibility function. This is the nonlinear force, and this is the output spectrum. Okay, we write the equation again, and then actually use this equation only cannot get the damage indicator. We found that the structure with the nonlinear boundary is a nonlinear system. So if we change the magnitude of the input excitation, then we can get four equations similar to equation 6. And then if we extract three of them, then we can get two groups of equation shown in equation 8. And with the inverse matrix, then we can get another equation. And the detailed expressions of this vector and matrix are shown here. And this is the structure parameters vector, and these two terms are caused by the nonlinear forces, and these are the transmissibility function matrix, and this is the structure parameter vector as well, this term. And then, and if u equals to 1, then we can get one equation to calculate the second term and the third term. And with these two equations will define one fault feature. Actually, this feature is defined by as the ratio of these terms. On the other hand, it can also be calculated by transmissibility functions. And similarly, if we use equals to 2, then we can get another fault feature. And with two fault features, we can get a lower damage indicator. Okay, let's explain the basic principle. Here, if there is no fault in the structure, then related terms in these two vectors will be 0. Then the two fault features will have the same expression, which means the fault indicator will be 0. On the other hand, if there is fault in the structure, then the two fault features will have different expressions. Then which in turn lead to non-zero fault indicator. So we can complete the fault detection and localization based on the value of the fault indicator. On the other hand, we can find that these two fault features are calculated by these two terms. Actually, these are the elements from the matrix B, and it can be calculated from the transmissibility function matrix. So which means in the practical application, we can use the output responses to calculate the transmissibility function, then to calculate the related elements C, and then to obtain the fault features and fault indicator. And based on this, we propose one novel method, and its procedures are shown here. Firstly, we need to find the T-type substructure, and then excite the structure with the shaker 4 times with different magnitude, and to collect and process the data to calculate fault features and fault indicator, and to decide whether there is a fault in the structure based on the value of the fault indicator. And this is the experimental testing devices in our lab, and this is the sensor for the data collection. This is the mass, this is the bolt collection, and this is the excitation produced by this shaker. And there are 3 states of structure are considered. For the health structure, all bolts between masses are tightened, which means there is no bolt losing force in the structure. And these terms are used to simulate nonlinear boundaries. And in case 1, we find 2 P-type substructures in the structure. One is here and one is here. In case 1, there is one fault in P-type structure A, and in case 2, both P-type structures have both losing force. And let's check the result. For case 1, this is the fault feature, and this is the depth indicator. And for case 2, we can get the similar results. And for case 1, we can find that for mass 10 in substructure A, we can find the fault indicator is relatively large. So we can obtain the result that there is one bolt losing force in this T-type substructure A. And for case 2, we can find that both indicators are comparatively larger, and we can obtain the result that both substructures have fault. And for the conclusion and discussion, actually from the theoretical analysis and experimental verification, we decompose the complex aerospace structures into some simple T-type structures, and then we use the theoretical analysis for the derivation of fault feature and fault indicator. And then we excite the structure 4 times with different excitation magnitude, then we can get the related results. And our results are verified through the experimental verification. And for the extension of this structure, I will show you a video. And this is a router. to simulate high pressure rotor in the aero engine, and it has one shaft and two teeth. And this is the sensor. And this is the support. And this is for the sensor setup. In case one, there is no moving force. Then we will collect the data for the following process. In case two, and in case two, this one has some both moving force. Then we will grab the router and to collect the related data. Okay, in case three, we consider more complex situations. This one has some rotary force. This is similar to the to that in case two. Okay, apart from that, this two also has some rotary force. And we need to collect the data again and to calculate the force indicator to decide the calculation of the both force. Okay, there are some references. Okay, thank you very much. Thank you very much.
And answer sessions. Again, for the online audience, please put down your questions by using the Q&A feature on your screen. We will attend to your questions shortly. May I first invite our audience on the floor to ask any questions you may have? Any questions?
Yes, I have one simple question. May I know why aerospace structures can be simplified by some T-type substructures?
Okay, thank you for your question. Actually, since the real aerospace structure is very complex with the different types of structures, and we found that most of bulky structures are very simple T-type or other simple structures such as the beam-like, the drone type, or some other structures. So we want to simplify the operation. We don't want to consider the whole structure, so we only consider the simplified T substructure. And here actually we only for the T-type substructure we only consider the local error. We can find that for these 2 degrees of freedom there are also some other parts. But for this part, so we only need these 4 output responses for the force diagnosis of this local error. If we want to consider other errors, we can only use the similar process and to diagnose other parts. So our idea is to consider the local error and use the output responses of the local error for the whole structure. Okay, thank you.
Okay, maybe I have one question. In your experimental setup, you show that you test the uh, the joint, okay, based on a rotating shaft.
Oh, no. For the this is the experimental verification for the method in the paper, and this one is for our current research. We want to extend the current method to the rotating structure. It would be more complicated, but we think that the method would be very similar, and so after the application, our method can be applied to um, many different structures.
Okay. So in your experimental test, you did test under some dynamic conditions, in
Yes,
stress and strain.
yes. For this part, actually, this is a structure and to simulate the aerospace structure. And here we use the shaker to excite the structure, which means we can collect the output responses and use the shaker to produce the excitation to simulate the dynamic environment, such as the vibration force or some other types of forces.
And you use this experimental results to verify your modeling performance. What compare the errors between the theoretical results and the experimental measurements?
Yes, this is just for the verification. Actually, we did this experiment in the lab. We also wanted to apply our method to the real structure, but maybe in the future.
Okay. And my last question is, did you apply your novelty, okay, this technology, really on the a space project?
No, we just completed the experiments in the lab. Actually, for the real structure, it needed to consider many things, such as the structure itself and the testing devices and the testing conditions. So we want to apply the method for to the real structure, but maybe there are some other problems we need to consider in advance.
Okay, thank you. And
Okay, thank you, Sharma. Thank you.
and okay, any more questions? Okay, as there are no more questions, we will proceed to the presentation of the next award paper. Okay, and now let me introduce our last awardee of today's lecture, Miss LAM Ying Tung. Miss Lam is a graduate of the Hong Kong Polytechnic University, major in building services engineering. She's unable to join us this evening and have pre-recorded her presentation on her awarded paper, and the title is The Study of Fire's Impact on Glass Panels. We will now play the video, and I hope you enjoy her presentation.
Good evening, ladies and gentlemen. My name is LAM Ying Tung, and you can call me Doremi. Before kickstarting my presentation, I'd like to express my heartfelt gratitude to Hong Kong IE for selecting my research paper as one of the outstanding paper awards this year, and further extend my gratitude to Dr. Li Ming from PolyU for his guidance and support throughout this research. The topic I'm going to share with you tonight is the fire impacts on glass panels. So I will split my presentation into 5 parts. I will begin with reviewing on the topic's background and its significance, followed by the research gap and objectives, then methodology, analysis and discussion, and lastly, an optimal glass protocol would be proposed. Having one of the most iconic skylines in the world, Hong Kong is densely packed with tall buildings. In fact, there are more than 9,000 high-rise buildings erected in the city, and among these buildings, 4,000 of them are skyscrapers that are taller than 100 meters. In order to achieve energy efficiency, glass facade is widely used in modern buildings nowadays. Moreover, people nowadays are looking for a larger open plan area, and at the same time, engineers gradually apply timber as a construction material, which alters the fire development when compared to the compartment fires occurred decades ago. As fire safety is of essential need to buildings, and therefore, we have to combat different fire behaviors evolving over time by obtaining a fire-safe glass facade. It is quite sad to say that there are lots of fire accidents take place around the world every day, while some are really devastating, such as the World Trade Center 7 fire in the US and the Grenfell Tower fire in the UK, which show the fire development in a large compartment. For a small compartment fire, we can observe the fire behavior through these two heartbreaking fire accidents in Hong Kong, like the residence fire happened in Kwun Tong in 2015 and the rim fire occurred in Kwai Chung in 2021. So, what do we know about glass in fire? We normally have a false perception of glass that it is a tough material. Actually, it is very fragile, especially under a building fire. Under the conditions that smaller glass panes are stiffer and smaller wind speed slows down the formation of cracks. In general, currently used tempered glass panels breaks at 357 degrees Celsius, and energy-efficient glasses like the low E glass cracks when the temperature difference between the glass center and edges reaches 108 degrees Celsius. That initiates the crack formation in glass, and eventually the glass falls out. Fire will then penetrate and spread into the adjacent floors along the facades as illustrated by the pictures on the right-hand side. In light of the previous fire accidents, I would like to bring the emphasis on the real fire impact imposed on glass panels and its breakage for both small and large compartments, and subsequently develop a more fireproof glass facade system to enhance fire safety. In this research, I set up numerical simulation models on PyroSim to analyze the fire behavior via FDS, which visualizes how much energy being absorbed by the glass and smoke movement, etc. Thus, experimental tests will also be conducted at PolyU laboratory to test the glass panels under different realistic fire impact in modern building compartments to obtain a fire-safe glass system. I have set up a generic two-story compartment model on PyroSim at a team-owned workstation for computation at PolyU. A total of 8 scenarios of compartment fire were simulated with different compartment sizes, fire locations, and glass panel sizes, and they were arranged like the 4 models shown on the right. Since heat is transferred from flames and hot gases to the surfaces of the glass windows via radiation and convection, in these PyroSim simulations, solid-phase devices like gauge heat flux and adiabatic surface temperature were utilized as they take radiative heat transfer into account when compared to the gas-phase devices. The diagrams on the right-hand side reflect the allocation of the devices, where the upper one shows the front view of the two-story compartment and the lower one illustrates the aerial view of the fire floor. Integrating the simulation results done by FDS, multiple fire tests were performed in the fire engineering laboratory at PolyU. For the experimental test, a single-story compartment made of asbestos boards was erected for thermal insulation. This rectangular compartment remains open to simulate a large compartment fire. As demonstrated in the photo on the right, glass varying in 2 sizes were installed on the compartment and a propanol pool fire was set at a distance to the glass. The 12 fire scenarios were listed in the table below here. For the data collection, 11K type thermocouples were installed on the glass and 2 thin-skin calorimeters were embedded right next to the glass. They were connected to a data logger to visualize the data collected. In addition, 2 cameras were recording both front view and side view of the fire development. Here summarizes the glass breakage time for the 8 scenarios, and they reflect the importance of fire location and the compartment size in fire development. The closer the fire source and the smaller the compartment, the faster the glass breakage, which contributes to the vertical fire spread. These 2 simulations compared the difference of fire behaviors in a small room and a more than large room. We can see the upper glass breaks when a small compartment fire takes place, and there are comparatively severe external fire impacts after the early glass breakage in small compartments. We can note that early breakage of glass panels can significantly reduce the fire impact of modern large compartment fire, and glass breakage can be caused by external fire flames, such that fire will then be spread to the upper floors. These 2 graphs illustrated the effect of breakage time on internal fire development, where the darker curves indicate the heat flux record when an early glass breakage takes place. In small compartments, certain ventilation to the under-ventilated fire by an early glass breakage favors ventilation-induced flashover and brings severe fire impacts to the upper floor, just like the simulation demonstrated just now. However, an early breakage in large compartments helps lower the fire intensity by providing ventilation to the fire. And the upper large story also suffer less intense external fire impacts due to the early breakage. Differing in compartment size, fire mainly develops out of the small compartments as vertical fire, while fire mainly grows within the large compartment. As you can see on the right-hand side of the slide, flames climb up and penetrate to the adjacent floors in small compartments, while scattered smoke contacts the upper glass 5 minutes after the ignition. The gray lines in these graphs indicate the internal fire development within small compartments. Regardless of glass size, small compartments were having a minor internal fire development, while fire within large compartments were vigorous. Additionally, the difference in heat flux encountered by the glasses is also small in small compartments. Along with a smaller difference in AHD, we can conclude that minor heat loss is found in vertical fire in small compartment fires after glass breakage. The simulation also draws a distinction between glass sizes in fire development. Fire breaking out from small windows develops along the facade, while a large one drives the fire away from the building envelope. The curves also support that the heat being transferred to the upper glass was more intact due to a small glass breakage. In the experimental test, we can observe that a closer ignition fosters glass breakage and fire blasts intermittently due to the glass cracks. As shown by the peaks in the above heat flux curves, remarkably, we can also see the effect of glass breakage in the fire development in this real fire test. Owing to the fact that smaller pane size differs, its higher fire resistance postponed the breakage. However, the temperature distribution shown between the center and the edges is larger in small glasses, which challenges the former researchers. Despite glass size, fire also blasts intermittently after glass breakage. Within my research, 3 limitations are resulted. For the computational modeling, wind load was not being taken into account, which should speed up the glass breakage in fires. For the experimental test, a propanol pool fire was used, which is relatively unstable and uncontrollable in directions. To stabilize the heat input, radiant panel could be used to adjust the heat acting on the glass panels. Radiation errors are also inevitable under the asbestos suspending environment that may cause excessive radiation, although radiation corrections have been taken into consideration with reference to the engineering models. The actual incident heat flux on glass could not be displayed in our experiments. Integrating the above findings, an ideal glass panel in modern buildings can be concluded as resistant to external fire and sensitive to internal fire. Under these two principles, I set up a model on Pyrosim to support this proposal, where the yellow lines indicate the heat flux record on the optimal glass. Both stories resulted in a less severe fire impacts under an ideal glass. Summing up my research done here, the time taken for the glass breakage is very crucial when evaluating the fire impacts in small or large compartments. Also, fire grows in different directions on the account of compartment size. Notably, glass size dominates the trajectory of vertical fire, where fire develops along the facade after breaking out from small windows. Ultimately, an optimal glass protocol was proposed that an ideal glass should be sensitive to internal fire and resilient to external fire. This brings to an end of my presentation. Thank you so much for your time. And if you have any inquiries regarding this topic and would like to discuss further, please do not hesitate to drop me a message. Thank you so much and hope you all have an enjoyable night.
Okay, thank you, Miss LAM Ying Tung. So if you have any questions about her presentation, you may contact Miss Lam directly. Okay, now let me give a closing remark. All the awarded papers have been presented. I would like to extend my heartfelt gratitude to all the awardees who have dedicated their time and expertise to present their remarkable papers. Your contributions have truly enriched this event and inspired all of us. Two of the awarded papers presented today have already been published in the awarded issue of the Hong Kong IE Transactions and will be followed by the shortlisted papers later this month. If you are interested in reading the awarded papers in detail, you are welcome to visit our Hong Kong IE Transaction website. Looking ahead, I'm delighted to announce that the Hong Kong IE Outstanding Paper Award for Young Engineers and Researchers 2024 is now open for paper submissions. I encourage all aspiring young engineers and researchers to seize this opportunity and share their research accomplishments. Let's continue to foster innovation and excellence in engineering. Goodbye, and hope to see you again next year.